Welcome to section 6.4, exponential and logarithmic equations. So we've alluded to it so far in this chapter, but in this section we're actually going to pin down some solid procedures for solving exponential equations, and at the end of the section we'll look at how to solve logarithmic equations. The primary theorem that will allow us to solve exponential equations in this section is the exponential equality property. We'll, when I refer to it, call the EEP. This theorem states that given a base b greater than 0 and not 1, if we have the following equality, b to the m equals b to the n, then we can conclude that m equals n. So this first equation is true if and only if this second equation is true. This makes sense if we look at an example. If I say that 3 to the x equals 3 squared, it's easy to see that the right-hand side is 9, and I am asking what power does 3 need to be raised to give me 9? X equals 2. So, the way that we are going to use this property to solve an exponential equation, that is, an equation where the unknown value is in the exponent, is first we will try to express it as the same base on each side. So we will somehow convert or manipulate the left and right-hand sides of the equation so that they are expressed in terms of the same base. Once we've done that, we can use the exponential equality property to equate the exponents. From there, we should be able to solve the resulting equation using techniques that we have seen in the past. And finally, it might not be a bad idea to check the answers that we find. So an example of this process, suppose that we are told that 3 to the 2x plus 1 equals 9 to the 3x. Now I need to figure out what x would make both sides of this equation equal to each other. So using this procedure, first I would like to express both sides in terms of the same base. And I'm noticing that the left-hand side has a base of 3, the right-hand side currently has a base of 9. But 9 is a power of 3. So if I were to convert that 9 and call it 3 squared, we're making progress. Now, if I apply the power to a power rule of exponents, I can see that this equation can be written as 3 to the 2x plus 1 on the left, and 3 to the 2 times 3x, in other words 3 to the 6x, on the right-hand side. Now I have the base to one power equals the base to another power, and I can infer using the exponential equality property that these powers must be equal to each other. I'm left with a linear equation in terms of x that I can easily solve by, for instance, subtracting 2x from both sides, isolating x on one side of my equation. And if I divide both sides by 4 at this point, we see that x equals 1/4. Now, to double check this, you can either substitute x equals 1/4 back into your equation. So my left-hand side would be 3 to the 2 times 1/4 plus 1. And my right-hand side would be 9 to the 3 times 1/4. And I can simplify the left-hand side's exponent. 2 times 1/4 would be 1/2. So this would yield 3 to the 3/2. My right-hand side can be simplified as 9 to the 3/4, which is 9 cubed under the 4th root. And 3 to the 3/2 power is the square root of 3 cubed. Now if you plug both of those into your calculator, you will see that they are in fact equal. And so x equals 1/4 is the solution of this equation. Here we see another exponential equation, which we will use the same technique from the previous video to solve. Again, we want to express both sides of this equation in terms of the same base. Since all of the numbers that I see here are powers of 2, I am going to choose to let that base be 2. Now my left-hand side contains a factor as well as an exponential part, but that factor is also a power of 2. So if I rewrite the left-hand side as 2 squared times 2 to the m plus 1, I can also rewrite my right-hand side, recalling that 16 is the 4th power of 2, as 2 to the 4th to the m minus 1. Now, using the product property of exponents, I have 2 to the 2nd times 2 to the m plus 1. I can combine these into a single exponential expression with a base of 2 by adding the powers. And on the right-hand side, I can use the power to a power rule, which says that 2 to the 4th to the m minus 1 is equivalent to 2 to the 4 times m minus 1. Each side of this can be simplified further, but at this point we have equal bases on both sides, so I can use the exponential equality property to say that the exponents must be equal. In other words, 2 plus m plus 1 is equal to 4 times m minus 1. And again, I'm left with a simple linear equation to solve. If I simplify the left-hand side, I see that m plus 3 is equal to The simplified right-hand side will involve distributing the 4, and will give me 4m minus 4. Now, if I subtract m from both sides, and I add 4, I will get 7 on the left-hand side, and 3m on the right-hand side, leading me to conclude that m is 7/3. Now the procedure that we used in this example will work as long as we are somehow able to express both sides in terms of the same base. This is not always as simple as it sounds. But if we are in another special case, if the exponential part of our equation involves a base of 10 or a base of e, then we can use a slightly more powerful procedure. We begin by isolating the exponential term. On one side of the equation. If there's more than one exponential term, we need to combine them in some way. We can then convert our equation to log form. At this point, we will have an equation involving either the common log or the natural log. So we can solve the resulting equation for the variable in question. And finally, we can plug that value into our calculator and check. Here we have an example of exactly this type of equation. We have an exponential equation, albeit a complex one, where the only exponential part of the equation involves a base of 10. My first order of business is to isolate that exponential term. I can do this by first dividing both sides by 40. Leaving me 3.5 minus 10 to the 2x on the left, and 65 over 40 on the right. I calculate this value to be 1.625. From there, I need to move the 3.5 over as well, resulting in negative 10 to the 2x on the left, and negative 1.875 on the right. Finally, if I multiply both sides by a negative value, I will get 10 to the 2x equals 1.875. I am finished with step 1. Now I will convert this equation to a log equation by saying that log base 10 of 1.875 equals my exponent 2x. Finally, the only thing that I need to do to solve for x is to divide both sides of this equation by 2. So we see that x equals log, and remember we can drop the base there, of 1.875 over 2. If I plug this into my calculator, I find an answer of approximately 0.1365. However, we could leave our answer in these terms. In terms of the logarithm, we have the exact definition of our answer. We can check by plugging either one of these values in as the exponent. So, if you evaluate 40 times 3.5 minus 10 to the 2 times 0.1365, you will arrive at approximately 65. We have already seen several properties of logarithms which hold for any base and any input. For instance, our first property says that log with any base of 1 is 0. We also saw that log with any base of that base is 1. And log base b of b to the x is x. Now this one is true for all x. In the real numbers. Our fourth rule says that if we raise a base to the log with that same base of x, we also get x. Several of these are based off of laws of exponents. There are 3 more very useful properties of logarithms. So if we consider 2 more variables, m and n, that are both restricted to being positive, non-zero, then the following must hold. Log base b of the product m times n is equal to the sum of 2 logarithms, log base b of m plus log base b of n. We call this property the product property. Second, we have what's called the quotient property, which says that log base b of the quotient m over n can be written as log base b of m, the numerator, minus log base b of n, the denominator. Our third new property of logarithms is known as the power property. And it says that log base b of an exponential expression m to the k can be written as k times log base b of m by itself. In other words, we can pull out that value k. You can find proof of these fundamental properties of logs on page 572 of our text. Along with a cautionary note, the following are common pitfalls that you would like to avoid. The quantity log base b of m times n is not generally equal to log base b of m times log base b of n. Similarly, log base b of m plus n is not equal to log base b of m plus log base b of n. Likewise, log base b of m minus n is not generally equal to log base b of m minus log base b of n. And the ratio log base b of m over n is not equal to log base b of m over log base b of n. Essentially, what each of these inequalities states is that logarithms do not distribute over multiplication, addition, subtraction, or quotients. Let us begin by using some of these properties to solve equations and simplify expressions. For example, if I know that log base 2 of 5 equals 2.3219 and log base 2 of 9 equals 3.1699, I can use properties of logarithms to evaluate the following. Log base 2 of 45, log base 2 of 25, and log base 2 of 9/5. To simplify our first example, I need to notice that 45 is the product of 5 and 9. I can then apply the first fundamental property to write this as the sum log base 2 of 5 plus log base 2 of 9, both of which I know the value of. I can calculate the sum of these to be 5.4918. In our second example, I would notice that I know what log base 2 of 5 is, and here I'm asked what log base 2 of 25 is. Now I know that 5 is 5 squared, or 25 is 5 squared. And so I can make the appropriate replacement. Then, using the third fundamental property of logarithms, the power property, I can pull this 2 outside and say that log base 2 of 5 squared is equal to 2 times log base 2 of 5 by itself. Again, since I already know what log base 2 of 5 is, I can substitute its value in and perform that calculation. arriving at the value of 4.6438. Finally, for our third example, I see that I'm asked about the ratio of 9/5 inside the logarithm. I remember that our second property of logarithm, our fundamental property of logarithms, says that I can break this up as log base 2 of the numerator, 9, minus log base 2 of the denominator, 5. Substituting these values in, 3.1699 minus 2.3219, I find 0.848. At this time, we don't have a very good way of checking these, but we will get one at the end of this section. Before we can begin solving logarithmic equations, we will need to get a little bit of practice manipulating logarithmic expressions. Our purpose is often going to involve combining logarithms into a single logarithm. We can do this whenever our logarithms have the same base using those three fundamental properties. For example, in this expression, 4 log base 6 of 18 minus log base 6 of 7, we can notice that my first term has a factor of 4 in it. Since I'm multiplying a logarithm by a constant, I can use the third property in reverse and pull that 4 inside as an exponent. At this stage, I can see that I have a log base 6 of some input minus a log base 6 of some other input. Since I am subtracting two logarithms, I can combine them into a single log base 6, where the numerator is the argument of the first log, and I divide that by the argument of the second log. And here we have our original expression expressed as a single logarithm. In our second example, we would like to use the order of operations to simplify whenever possible. I have a few options at this point. I might begin by simplifying what's inside the brackets using the first fundamental property of logarithms. I can do this by saying that log base a of m plus log base a of n should be equal to the product inside. In other words, log base a of m times n. Now again, I notice that my first logarithm in the second line has a factor of 1/2. So, as before, I can pull that 1/2 in as an exponent on the product inside the parentheses. So, the first term can be written as log base a of m times n to the 1/2 power minus log base a of x. Now I have a difference of logarithms, which I can again combine into a single logarithm. My numerator being what is inside my first logarithm, m times n all to the 1/2 power. My denominator being the argument of my second logarithm, in this case simply x. That that might be a good place to leave this one. Although, we should recall that the 1/2 power is actually the square root. So we could take this one step further and say this is actually log base A of the square root of m times n over x. It is a similar task to go in the other direction. In other words, to express a single logarithm with a complex argument as separate, simpler logarithms. This example is a little bit tricky. I see that I have the logarithm of a cube root of a ratio, of a quotient. So the first thing that I would like to do is express that cube root as the 1/3 power. Since the cube root is acting on the entire quotient a squared over b, the 1/3 power should apply to a squared over b. And that's why I need this set of parentheses. At this point, I can pull the power outside using the third fundamental property to say this is equal to 1/3 log of a squared over b. Now I notice that I have the logarithm of a ratio. So I can break that up, and remember this 1/3 is multiplying this logarithm, so it will multiply the two logarithms that it turns into. And finally, I can recognize that I have another exponent inside of this logarithm and pull it outside as a coefficient. So we might leave things there, or we could always distribute the 1/3 back in and leave our answer as 2/3 log of A minus 1/3 log of B. We can perform the same task with this second logarithm, in this case the natural log. Now, first and foremost, what is inside the parentheses of this logarithm, what is inside the argument, is a quotient. I would begin by breaking this apart as the difference of the numerator, x times y times z, and the natural log of the denominator, q squared. Now I notice that I have a product, x times y times z. So I could break this first logarithm up as the natural log of x plus the natural log of y times z. And secondly, this second logarithm has a power inside, which we can pull out as a coefficient. And finally, the ln of y times z can be broken apart. When I have a product inside, I can write it as a sum, ln of y plus ln of z minus 2 ln of q. Both of these techniques are useful in different ways. Being able to combine different logarithms into a single log will be very helpful in the next problem-solving procedure that we see. We have so far been unable to solve most exponential equations. We can solve ones where we are able to express both sides of the equation using the same base, and we have solved those where the base of the exponential portion of the equation was either 10 or e. But what about an equation along the lines of 2 to the x minus 5 equals 71? In this case, I have a base of 2 to worry about, and if I attempt to solve this using the procedures that we've seen so far, I would move the 5 over and see that our equation becomes 2 to the x equals 76. And since 76 is not a power of 2 that I can conceive of, I would have a very difficult time using the exponential equality property. So we need stronger tools. Our final procedure for solving exponential equations will always work. First, we isolate the exponential part of the equation. If at all possible. Next, we will take the logarithm of both sides. And we may use whichever logarithm we like. If we would like to use the log base 10 or the natural log, we will be able to do so. Finally, we can apply the power property. This will enable us to remove the exponent, pull it outside of the logarithm as a coefficient. And last, we will solve the resulting equation for the variable of interest. So returning to the example we were looking at, if 2 to the x equals 76, and I log both sides, at this point, I may use the exponential property, the power property, to pull x out front. And the resulting equation is x log of 2 equals log of 76. Now, all that I need to do to solve for x is to divide both sides by log of 2. I see that the log of 2's cancel on the left-hand side, and x is equal to log of 76 over log of 2. A quick check in my calculator indicates that this is approximately 6.2479275. We can check our work in the original equation by plugging 6.2479275 in for x. And plugging this value in, I see that this equality is valid. As with exponential equations, we have a notion of equality between logarithms. So given positive numbers m and n and b, with the condition that b is not 1, if log base b of m equals log base b of n, then we can infer that m equals n. This theorem affords us a bit of a shortcut. For example, if I have an equation of the form log base 9 of 3x minus 1 equals log base 9 of 5x, then I can say, since our bases are equal, that 3x minus 1 equals 5x. At this point, I can solve for x by subtracting 3x from both sides, and dividing both sides by 2 to see that x equals negative 1/2. I'll check and make sure these solutions work. Is log base 9 of 3 times negative 1/2 minus 1 equal to log base 9 of 5 times negative 1/2? Well, my argument on the left-hand side is negative 3/2 minus 1, which is negative. Negative 3/2 minus 1 would be negative 5/2. And we see on the right-hand side that 5 times negative 1/2 is negative 1/2, or 5/2, pardon me. However, both of these are undefined. So, this x value that we found is not in the domain of either of the sides of my equation. In other words, this is an extraneous solution. What I can take away from that is that this equation has no solution. So, with this type of equation, if I have logarithms, I always have to make sure that I'm not plugging in negatives or 0. So, we have an alternate procedure for solving logarithmic equations. First, we isolate the logarithm. Now I say the logarithm. If there's more than one, we want to combine our logarithms down into a single log, and the other side of our equation should not have any logs at all. Once we have a logarithmic equation of the form log base b of x equals y, we'll convert this to an exponential equation, just as we have before. Then we'll solve for the variable. And finally, we will always check for extraneous solutions. It is necessary with this type of problem. You absolutely have to check. An example of how we would use this procedure, if I have the equation log of x minus 1/2 equals 1 minus log of 2x, I'll begin by gathering all of my logarithms on one side. It will probably be easiest for me to add the log of 2x to both sides. So my right-hand side is 1. My left-hand side is log of x minus 1/2 plus log of 2x. Now I can use properties of logarithms to combine my left-hand side into a single log. Remember, if I have a sum of logarithms with the same base, in this case our base is 10, so we're good, I can combine these into a single logarithm where I multiply the arguments of each logarithm. So, I can simplify this to say that log of 2x squared minus 1/2 times 2x would give me x equals 1. Now I'll convert this to an exponential equation. Remember, when I have no base specified, there is an implied 10 as our base. So our base in the exponential version will be 10. My exponent will be 1, and my argument will be 2x squared minus x. So, I see that the equation I need to solve now is 2x squared minus x equals 10, a basic quadratic. So, I might gather all my terms on one side, put this in standard form. 0 equals 2x squared minus x minus 10. And we can solve this using any of our preferred techniques from Chapter 4. I'm going to go with the AC method. I notice that 2 times negative 10 is negative 20. One factorization of which would be negative 5 and positive 4. So, I will break up the middle term of my equation, call this negative 5x plus 4x minus 10, and then factor by grouping. So I see I can get a x out of every piece of my first two terms, and I'll be left with 2x minus 5. And I can get a 2 out of my remaining two terms, and be left with 2x minus 5. So my final factorization of x plus 2, 2x minus 5, indicates that x equals negative 2 and x equals 5/2. I now must check both of these. Well, negative 2 poses an interesting problem. Log of negative 2 minus 1/2 is clearly undefined, since negative 2 minus 1/2 is negative. So negative 2 is immediately recognizable as an extraneous solution. Let's try x equals 5/2. So log of 5/2 minus 1/2, is that equal to 1 minus log of 2 times 5/2? Well, if I simplify the left-hand side, I have log of 4/2, which is log of 2, And on the right-hand side, I have 1 minus log of 2 times 5/2. My 2's can cancel, and I'll be left with log of 5. Since log, with a base of 10, in this case, is a button on my calculator, I'll go ahead and plug these both in. For the left-hand side, I see that this log of 2 is approximately 0.301029996. And my right-hand side is the same. So we have a winner in x equals 5/2. Up until now, we've been able to successfully evaluate logs base e and base 10 in our calculator. But how would I evaluate something like log base 3 of 71? The change of base formula is going to help us convert this into something involving logarithms with bases that our calculator can handle. So, suppose we have a logarithmic equation, say y equals log base b of m, where m is greater than 0, b is greater than 0, and not equal to 1. Then we can infer the exponential equation b to the y equals m. And now we'll solve this equation by logging both sides using a logarithm with a base of our choosing. We've just seen that to solve this type of equation, we can common log both sides, or we can ln both sides, or we could use a base that is convenient for us. Any base will do. But from here, we can see that the power property can bring that y down as a coefficient, and the left-hand side will evaluate to log base a of b, and the right-hand side will remain the same. From here, we can solve for y by dividing by log base a of b on both sides. So y equals log base a of m over log base a of b. So to restate our original assertion, y equals log base b of m, we can convert this into an expression involving logarithms of our choosing as log base a of the argument m over log base a of the original base b. So for example, we could convert the expression log base 3 of 71 into an expression involving logs base 10. And both parts of this ratio can be evaluated in the calculator. I am finding that the log of 71 is approximately 1.851258349, and the logarithm of 3, the common log that is 0.477121 2547. The quotient evaluates to approximately 3.880058,435. And that is our approximation of log base 3 of 71. So this final formula finally allows us to check all kinds of logarithms, no matter what my base. Now, I can convert this into log base whatever I would like. So we could, instead of log base 10, we could have used log base e, the other logarithm that our calculator is equipped with. So instead of log base 10, I could say ln of 71 over ln of 3. Now, my numerator and denominator will be a little bit different. I find my numerator to be 4.262679877, and my denominator to be 1.098612289. But the ratio of these two numbers is exactly the same. So it does not matter what new base you choose, as long as everything makes it to where it's supposed to go. The argument goes into the numerator log, the old base goes into the denominator log. You can see that in both of these examples. And that is the last of the topics out of 6.4. Please get started on the homework out of this section and bring any questions you have to class.